Thank you, Chelsea. It's a great pleasure for me to introduce the next plenary that will be given by Alessandro De Luca. Alessandro is a true pioneer of robotic control. He got his PhD back in the early end of the 80s, I would say. But he's not a pioneer just because of that. He started working on flexible robots, and then after a postdoc at RPI in the United States, he worked on flexible and elastic joints for years. And then he really put the foundations for control of underactuated robots, which turned out throughout the years to be one of the main fundamental topics of research in our community. And I will argue in a minute. He then went to studying the theory of the nonlinear control of these systems. And just to mention, in 1998, he got the best paper award at ICRA, together with a paper introducing Asimo for the first time. So a purely theoretical paper was ranked as high as the Asimo, which was a big hit in robotics. And this, I think, is important for our community to recognize that theory is as important as practice and introduction of experimental. So in the rest of his career, Alessandro started doing applications of this method to robots that are compliant, physical human-robot interaction, and he was one of the pioneers with his projects, including Safari, for instance, of the PHRI interaction. That led to the fact that in Europe, cooperative robotics is really one of the, Europe is one of the strongest in the world for cooperative robotics, and that was due to the research that people like Alessandro did in this field. When you need something done right, you go to Alessandro papers and you get it right. So for instance, look at the reverse priority solution to the stack of task problem, and you'll find a very efficient and very correct solution that solves many problems that you can find in other situations. So Alessandro, I think it's very clear that Alessandro is not only my very good friend, but he's also one of the persons that I esteem most in our community, and I would like to invite him to give this talk.
Non credo che mi serva. Okay, thank you, Antonio. I think that everybody understood that you're a very good friend of mine, because you didn't mention the exact date of my PhD, especially. Okay, so thank you for inviting me to give this keynote speech. I'm quite excited because my feeling is that this community, it's a robotic community, but not really the one that I'm used to talk to. So I try to be as clear as possible, but I apologize for not being in advance. So, control of soft joint robots with some application to save physical human-robot interaction. So the outline of my talk will be just discussing what are the classes of soft robots that are around. There are many names. Sometimes things are equivalent, sometimes they are different structurally from the control point of view. I will show why we have used and we are using lightweight robots with flexible joints to do the best that we can for physical human-robot interaction. And then I will present some easy modeling stuff on a particular class of soft robots, those that have flexibility concentrated in the joints or in the transmission. And for this class, I will just outline what is the classic theory of control for solving the conventional task that every robot should do, namely going to a certain configuration, so a regulation task under gravity or without gravity, or following a trajectory defined in the Cartesian, in the task, in the joint space, whatever. So, and for doing this, I will use the classical tools. Why I'm introducing this? Because the second part of the talk will be revisiting all these things for the whole class of soft robots, including also those with joint elasticity. So we notice that there is a kind of a contradiction in how we have handled for years, for decades, flexibility in these systems. And so there are new ideas coming on, and I will present my own ideas and also some of our colleagues going through, if time allows, 4 examples of this type of new idea, which is essentially, I recollect it, although my colleagues don't call it like this, as the use of feedback equivalence. So it's an attempt of merging, for those of you who are familiar with this topic, a pure model-based feedback linearization technique, like the one that we have heard before, so transformation through feedback of the dynamics of the system until we get a very nice controllable linear system that we can handle very easily. So this was one avenue. The other avenue said, no, you have to deal with the dynamics of the physical system. You have to exploit passivity. In this way, you're robust. You are no longer affected by uncertainty in your model, which is not true even for the passivity case. So there was these 2 schools that fight for decades. And I think that now on this particular case, so the case of soft robots, there could be some reunion from this point of views. And then I will give an outlook. So classes of soft robots. First of all, robot with elastic joints, not flexible, elastic, because we assume that flexibility is in the linear domain. Why do we build this? In fact, sometimes we don't build this on purpose. We have to deal with the presence of flexibility in the transmission because we are using high G ratio devices like harmonic drives, which introduce elasticity per se. And this is a way of absorbing energy. In fact, no matter where you put some compliance in your structure, on the coverage of your links or in the transmission or on both sides, then you're allowed, for instance, to absorb impact, so to absorb energy. In fact, in the case of elasticity at the joints, what you do is you decouple the inertia of the motors from the inertia of the links. So if you're able to build a system which has stiff links and joint elasticity, but lightweight link, in fact, then the heavier motor are detached from any effect of collision. So the robot will harm less whatever it hits, in particular humans around. And this was a main idea, probably the first idea for recovering the use of lightweight robot with joint elasticity in physical human-robot interaction. And of course, things do not come for free, so you have a more complex control problem. You need more sensor. For instance, you may need a jointer sensor or double the number of encoders at the joint, so one on the motor side, one on the link side, and so on. But all these ideas have gathered into industrial product eventually by Kuka and by Franca and Mika and so on, which are the so-called torque-controlled robots. Why they are torque-controlled? Because there is an internal loop which measures the transmitted torque across the elastic joints and then use it for realizing the task independently of the presence of friction for it, and so on. So there's another class that has been exploited, in particular also by Antonio very much in a European project, which is robot with variable stiffness actuation. So this class, you have for each joint, which is essentially flexible, but the flexibility can be modified online. So there's a second command, either in an agonistic-antagonistic mode or in a serial mode, that allows you to modify the actual stiffness of the joint, together with the fact that the joint moves and follows some trajectory. So you have a two-output control problem that you can adapt online. So why this situation is good? Well, essentially because you're able in this way to preserve performance and handle safety. So if you have a very sloppy, soft robot, then and it's light, you expect not to have many problems when it hits the environment, or in particular the human which is working nearby. Okay, but the price you pay is that you're not accurate as traditional industrial stiff robots are. So the idea of variable stiffness actuation, one idea is in fact to modify online to get performance when you need performance. For instance, when you're starting and you want to accelerate very fast. So you need to stiffen your joints and then relax the compliance of the joints when you're reaching high velocity, where the danger of doing some damage to the environment or to the human is higher. So there are other reasons why you can use variable stiffness actuation, and lately there has been also many other applications. The idea of storing energy and relaxing in an impulsive way, so that you can throw a ball 10 times longer than with a conventional actuation with the same amount of power, and things like that, and robustness to environment problem. Okay, so this is another thing. Then there are another class of soft robots are those in which flexibility is distributed along the links. Again, this is not really a choice in general. If you're familiar with the space shuttle manipulator system, this was a very long arm in space, so not subject to gravity, but needs to be teleoperated quite slowly, because otherwise, with its length and with its limited mass, but still quite heavy, was going to oscillate and vibrate, and this is not good. So you want to use lightweight material to save energy and cost, or you may have this situation of flexibility distributed along a link appearing in your operation because you're carrying heavy loads, and this is another situation. So the situation is quite similar because in the presence of link flexibility distributed along the various limbs, then you will lose accuracy in position. So you have a static deflection due to gravity. But also, when you're doing a fast trajectory, you will tend to oscillate. So you have a control problem, just like in the case of joint elasticity and of variable stiffness actuation as well. Here there's another problem, however. The fact that from the control point of view, you have a sort of non-collocation of what you like to control and where you apply your command inputs. Typically, if you think of a long, slender, flexible link, like my arm, you apply torque at the base, but you want to control the tip motion. And for those who are familiar with control theory, the linear transfer function that you can build upon is a non-minimum phase one. So it has zeros which have real positive real parts. So you cannot do inverse dynamics in the conventional sense, because otherwise this zero will become poles in the controller which are unstable, and you will have instability in the closed loop. So this is an additional phenomena that you can represent by saying, those systems, they move in the opposite direction with respect to the command. So if you're giving a torque at the base, the acceleration at the tip will be typically in the opposite direction. And this is unwheeling the fact that the system is non-minimum phase. Finally, Continuum soft robots. I think that this is a big community, growing community. You are familiar with the fact that Soft Robotics as a journal has the highest impact factor in the field, which is, for me, kind of surprising, but not too much. So many, these systems are represented by an infinite number of degrees of freedom in principle, or they are hyper-redundant in terms of degrees of freedom. And they have, again, distributed deformation. Here you can see a number of examples. One is biological, the other are bio-inspired. So this is another common technique. You see the famous octopus by Scuola Sant'Anna, and the elephant trunk by Jan Walker, one of the first that started doing this type of activity. And you have also an equivalent representation of this distributed flexibility in a continuum, where you can, in under certain assumption, you can match this with a finite dimensional model. I think I can skip this, but just to say, well, many different names, but sometimes things are the same. For instance, when we are talking about elastic joints or serial elastic actuation, they are exactly the same thing. The only difference is that elasticity in robots, in particular in industrial robots, joint elasticity, was seen at the beginning as a parasitic effect that should be discarded in the best way as possible, while serial elastic actuation was intended to include actuation. And this can be seen also from the range of typical stiffness value of an industrial robot with harmonic drives or a SEA research arm. So this is one comment. Second comment is that most of the time we consider flexibility in the linear domain, so we talk about elasticity, but many problems and many similar results hold also when you're dealing with nonlinear stiffness behavior. And finally, and as Antonio commented, this is, I think, a very interesting point. If you talk to control people, they say, okay, all those flexible systems of robots are under-actuated systems. Why? Because the number of generalized coordinate or degrees of freedom of the system is larger than the number of commands. So you cannot do whatever you wish, like in the case of rigid robot. So trajectories should be feasible according to the model and things like that. But this is not the whole story, because if you think about a simple mechanical system made by mass, a number of mass connected by springs, and with just one input on one side, and you're controlling the last mass in this series, well, it's not easy, but this is a linear controllable system, and you can do many, many things. Okay, so under-actuation is not the whole story, but under-actuation without the property of controllability in the first approximation, then the problem becomes very hard. And elasticity, at least in the joint elastic case, provides this linear controllability, and this is why also more complex nonlinear control design can be implemented. Okay, so in this video, I try to show the classical problem that you have in the presence of joint elasticity. You can see an industrial robot, a heavy one, a KUKA. You can see the lightweight KUKA arm, actually the DLR, and then also an academic example by Quansar, where you have, in fact, on one side the motor, which is being held fixed in all these cases, or oscillating at a given frequency in the last case, and on the other side you have the link side of the elasticity, which vibrates because it's actually not controlled unless you model what is going on. And when you model, you can also counteract with feed-forward or feedback strategies. Okay, so this is just as an introduction. And this is one video, or only two videos in my lab, where we were using the lightweight KUKA arm to do physical human-robot interaction. And we can do this in a very efficient way because we have a good model and because of the presence of joint elasticity, which is able to decouple all the effect between the links dynamics and the motor dynamics. In particular, in this case, without having a force-torque sensor and using the so-called residual, for those of you who know this type of work, we are able to detect collision at any place in the structure and also distinguish if it's a soft or if it's a hard collision. If it's a hard collision, like in the first place, then the robot goes away. If it's soft, then it engages a collaboration phase where forces are exchanged, and in fact, they are actually measured and controlled. In fact, here I show a ICRA 2015 result, Again, you can see a depth view of the robot. You can see also a red line, which is where we detect the contact based on external measurement, 1 or 2 kinects, and internal model-based computation, which is the residual signal. When both of them tells us that something is going on, we localize the contact point. We have an estimate of the resulting joint torque from the applied force by the human, and so we can estimate also the intensity and direction of the contact force. And once we have this estimation without a force torque sensor, we can regulate this force, for instance, here at 50 newtons. And we can do also impedance control, we can do a hybrid force velocity control, but at the contact point, not at the end effector or at the joint space like it's traditional when you're having joint torque sensor or force torque sensor at the end effector. Okay, so this is just as a motivation, one other motivation why we need to study this type of dynamic system. And I will start with this equation, which are quite fundamental. You don't have to go through, but just look at the assumption that we made, small displacement at the joints, the fact that the motors are axis balanced, and one important thing, we neglect internal coupling. This is a so-called reduced model introduced by Mark Spong in 1986. Okay, so this is quite at the time of my PhD thesis. So, and you can see that you have the upper part of the dynamics, which is called the link equation, which is exactly the dynamics of a rigid link robot, but without input torque, just with elastic torques, which is this product of k times q minus theta. Q and theta are the variable of the link and position, which is driving through flexibility the link dynamics. And then you have a very simple motor dynamics, which is most of the case linear. The B matrix is the inertia of the motors. It's typically diagonal. So you have a linear addition to the system. And on the on the left-hand side, actually, you have the input torque. So this is the classical model. Now, if you look at a single degree of freedom, a linear version of this, which is just given by an inertia or a mass B, which represents the motor, a spring K, a mass m, which represents the link, and you're acting on one side, but in fact you would like to control the position of the other side and react to environment forces applied to the link side of the problem. So this is a paradigmatic version of the multidimensional nonlinear case. In this case, you can work with linear transfer function, and you can recognize that if you're matching the torque, the input torque to the position of the motor, then the system can be shown to be passive. And in fact, it has 0 and a relative degree 2 for those who are familiar with this subject. But if you look at the same system and you're trying to reach the position of the link, then you have a strange phenomena. The zeros disappear. The relative degree, which is the difference between the degree of the denominator and the numerator of this transfer function, grows to its maximum, which is 4. This is, in fact, unveiling the fact that when you move to the nonlinear case, the system will be feedback linearizable. Okay, so I think I will skip this. You can recognize the presence of joint elasticity by looking at standard frequency response, like Bode plots, but this is not important now. So with this model, with the general model, you would like to do tracking. Follow a smooth trajectory, smooth enough trajectory, and apply some torques that realize this. We assume that we know perfectly the model. We have to identify it, of course. This is also true for the whole physical human-robot interaction that I've showed you. We have a very good model of the system, including friction and so on. So what you can do, you can compute a feed-forward term. So a command, which is the easiest way of solving the trajectory tracking case. Now, you do the computation. It's a long expression. In blue, it's the rigid part. So if the robot was rigid, so the joint stiffness was going to infinity, k, then you would have left only this part, which is computed typically with the Newton-Euler recursive numerical method. All the rest is coming because of the flexibility. And in fact, you can see that there's a big k to the minus 1 in front of the square bracket. So that signifies that in the limit you recover the rigid case. So you can do this, and you don't have problem of instability or else. But if you want to apply the same type of idea, starting from a different state, so not being matched initially with the desired trajectory, you need to use also feedback. And in particular, you can use feedback in a very general way, so by using a nonlinear law in terms of the measured state. And the way in which you derive this, you don't need to know the theory of Lie brackets and the involutivity and so on. You can proceed for this second-order mechanical system just by looking at the equation and taking as many derivatives as needed until you find the input explicitly appearing, and then you try to invert the system. So this is the main idea. In fact, if you take two derivatives of the link equation, which has a 0 on the left-hand side, so there's no input torque there, and then you substitute, you can achieve a behavior which is similar to the computed torque in the rigid case. The only difference is that you don't have the acceleration being controlled by the new input u, but you have the fourth derivative of the joint position. So you're controlling, in fact, the snap directly. So this has been criticized quite a lot because apart from the many computations that you have to do, but doing computation nowadays is not really a problem, okay? So I don't accept any comment on that any longer. So, but the other critic was you need higher derivative of Q, and who gives, there's no sensor measuring joint acceleration, even less joint jerk. But these, in fact, are not needed. You don't need to measure this. You just measure the position of the motor and of the link. If you want, you do numerical derivative in order to get the velocity, and that's the whole state information you need to implement this control law. And in fact, if you're scared about all these terms, you can have at disposition also a numerical method to compute this feedback linearization control. So a package which works wherever the robot is, no matter how many joints. Unfortunately, it grows with n cubed. The complexity is not linear like in the standard case, but the coefficient in front of the cube terms is very small. Okay, so with this technique, you have had, this is a seminal result. I found this video in the Springer Handbook of Robotics. So Mark Spong implemented first this feedback linearization, but first thing, he tried to implement it assuming that this device, experimental device, was rigid. Okay, and this is what happens, because you're feeding back not the motor position, but you're feeding back the link position, and because of this fourth order linkage, the closed loop becomes unstable. This is very surprising, in fact. Instead, if you're doing things in the right way, so you're implementing the full feedback linearization control, you have a perfect tracking of this smooth trajectory and then going back. And again, feedback linearization can be implemented also in systems more complex than that. Here you see the comparison of the previous industrial robot with a feedback linearization plus high damping injected on the linear side of the problem. And you can see the difference in this transient in response to an external force. But also while doing conventional tracking, you see on top the original KUKA controller and below the controller developed based on feedback linearization, and you can tell the difference. KUKA guys were not so happy when we showed this the first time, of course. They say, this is an old version of our controller. Okay, anyway, there are other things that you can do. For instance, if you have available a joint torque sensor, you can use this joint torque sensor, and this is not really for feedback linearization, but for doing a very interesting things. So for reducing the motor inertia. As I said, if you have a lightweight robot, so the link inertia is small, but the motor inertia continues to be dominant. And with this type of feedback, you can reduce at will the motor inertia so that the system becomes more and more close to the rigid case. So this is an interesting result by Christian Ott and Aline Albuchefer. Now, this is about tracking control. What about regulation? Typically, when you want to solve a regulation problem, you have a simpler control law. And in fact, this is the case here. And here I've listed a number of results that have been growing over the years from a colleague of mine, Patrizio Tomei, in 1991, who proved that a PD controller, in this case, plus constant compensation of gravity at the destination, is globally asymptotically stabilizing the closed-loop system, provided that the gain Kp of the proportional is large enough. In fact, it has to dominate this quantity, which is the bound on the norm of the gradient of the gravity terms, and also the stiffness is large enough. Now, over the years with colleagues and also with the group of DLR, we have been working in trying to relax this condition. In fact, the last known result, at least published in journal, was saying that if you do some kind of iterative update of the gravity term in the control law based only on motor position measurement, and you have a kind of contraction, then you can relax the condition on the proportional gain. It can be just positive, like in the rigid case, but still you need the stiffness of the joint to be larger than alpha, which dominates the gradient of the gravity. If you don't want to do that, then you can apply this exact gravity cancellation, which requires, however, full state feedback. And this is introducing my last part, so the idea of using feedback equivalence in order to obtain the least possible modification of your system which fits to your need. This is the take-home message, in a sense. You don't need really to cancel everything. You cancel only what you think is important to be canceled, and you use as much as possible the physical property of the system to preserve where they are needed. So the problem is exact gravity cancellation. This is really not a problem for the rigid case. Why? Because you have full actuation in the rigid case, so you have the model on the left-hand side, and I think there's no need of a robotics course to say that if you design tau by cancelling this G of Q and then adding whatever tau 0 for doing the rest of your task, you have exactly cancelled the gravity. So this is just the idea. So you like your robot, whatever dynamic it has, instead of behave as moving under gravity, it behaves like in a horizontal plane, okay? And this is possible, of course. It's trivial in a sense. But when you have joint elasticity, then the problem is not so trivial. So how to compute this tau g, so the term that removes gravity from the picture? And why there's a problem? The problem is quite evident because of non-collocation. So you have the torque is here, but the gravity is there, so you have to go through the elasticity in order to reach this upper equation and cancel out this gravity. So how do you do this? In fact, before doing this, the same problem occurs if you're having variable stiffness actuation. The equation looks very much similar. The only difference is that you have two motor equations for each joint, and this is the vector format for a generic set of n joints with variable stiffness actuation. Same problem. Is it possible to find input torques on the robot under gravity so that the robot behaves itself like the same robot without gravity? Okay, so the question is exactly the same. And the solution goes through this very simple argument. Suppose that you have a system, a nonlinear system on that side, which in this case is gravity loaded. It could be anything. It's your starting system. But you know that through a nonlinear feedback and a change of coordinate, you can transform this into a linear controllable form. And then you check if your target system, which in this case is a gravity-free system, is transformable into the same form. And then by simple composition, you just move directly from one to the other. So the existence of this feedback linearization property allows you to say that you can do something simpler if needed. Okay? It's a very simple concept. In fact, if you apply to our case, the result of doing this equivalence is that you cancel gravity, g of q, but you have to cancel also the first and second derivative of the gravity vector field multiplied by some the stiffness, the inverse of the stiffness gain. In fact, when k goes to infinity, you recover the standard case of the rigid joints. So I will skip this. And once you have done this, then you have left with a system that has no gravity any longer. So you can imagine, well, if there's no gravity, then a simple PD could solve the regulation problem without any extra condition. And this, in fact, it is true. The only things that you have to make sure is that you do the change of coordinates that is needed in order to have the same correspondence. In fact, you may imagine that even if my robot with flexible joint moving in a vertical field behaves exactly like this, this is true only from the outside point of view, only from the link side. But in fact, the motor inside are going to different trajectories which are needed in order to compensate the true gravity which is there. Okay, so if you're leaving a robot at rest like this, the position of the motor and the position of the link are the same. If you leave it under gravity, even if the link position are the same, the motor should be charged in order to compensate for the gravity. Okay, so there's an equivalence which is only in terms of a selected set of variables, which are the link variables. Okay, so with this controller, you can prove that you have global asymptotic stability under no special condition, neither on the proportional gain of the controller nor on the stiffness. And this is very valuable also for the variable stiffness case, because in that case, you may wish to bring the stiffness of the variable actuation joint at a very low level, okay, even below the presence of gravity. Okay, so again, I skip this, and this is the same result. Okay, just a note on the result. This is just a simulation on the result for the variable stiffness case. In this case, you have two so-called linearizing output. Remember that you have one joint, you have two input commands, two torques, the two motors that in this case are working in agonistic-antagonistic mode. So you have two sets of linearizing coordinates. What are these coordinates? Just like in the constant elasticity case, one is the position of the link, the other is the actual stiffness of the joint. So you have two outputs to be controlled. In fact, what you can do is to let the robot behave as if it was on a horizontal plane instead of moving in a vertical plane. And this output function reproduces exactly the one of the unloaded system, but internally, of course, the two motors are acting wildly in order to compensate for the presence of gravity. So this idea of canceling some remote term in the dynamic equation has been later on, much later, actually, this is work of 2017 and 18, by the group of DLR, very good friend of ours, actually, in order to solve a problem that they had with their variable stiffness upper torso. This device has changed name over the years. Now it's called David. It used to be called Hazy. I don't know why they are changing things, but anyway. So what they said, okay, they experienced that there was no way. They tried to do feedback linearization, too complex, too many uncertainties. So they say, how can we stop the link vibrating so much when we're doing our task? They had this problem. So they said, okay, instead of canceling gravity, we should add damping term on the link side. Okay, instead of taking out, putting in. Very simple idea. So you have the original model is the one on top and has no damping. Oh, sorry, no damping on the link side. And now the target model is just the same, but with an additional term here, a viscous damping. And now you can design your control. If the feedback control is the one, it's much simpler than feedback linearization. Even if you have uncertainty in the parameters, what will happen is that you're not really damping with the desired value of d, the motion of the link, but you're still damping. I mean, you have to have very large perturbation in order not to achieve damping under uncertain condition. So this idea is, again, an application of feedback equivalence, although They have called it elastic structure preserving control. And together with the feedback control, you have also the state transformation, which maps, in particular, the theta variable is the motor variable of the system without link damping, and theta 0 is the motor variable of the system which realize introduction of damping on the link side. So there's still the same concept of state transformation plus nonlinear feedback in order to achieve the result. And here I have a kindly offered by DLR nice video. You can see that on the this side is the situation in response to a force and the vibration that they have without this damping. And on this side, you have the same situation. You can move out the system very large from the rest position, and you don't see oscillation. Okay, system is nicely damped. So what about the fact that you really can interact with the environment? This is a third example, and I think that I'm almost done with this. So the idea is, okay, let's represent this on a simple 1 degree of freedom case. So we have the elastic joints. Now the additional part is the presence of the environment force here. Okay. Now if you try to invert the system, then you will end up with needing not only the measure of this external force, but also an information about its first and second time derivative. So impossible to have, or very noisy if you wish. So this is not the good idea. So the good idea is to have a target model which is exactly like the one that you're starting with, but with different parameters. So if you are familiar with the behavior of second-order mechanical system, mass spring dampers, you know that changing those parameters, you know everything about the system. Step response, overshooting, time to reach a steady state value, and so on. So you can choose your target model. Now, there's nobody, so far, we are working on that nowadays, that tells you what is the best reference model of the fourth order, which is the one that you are targeting in this case. Now, we realize that we need to make a restriction, so we cannot change the mass of the link side. So the M0 of our target should be exactly the same as the one of the original system. But this is the control law that achieves the goal. There's a second problem that you can formulate, a problem of optimal control. So if really your target, I mean, if your system is very bad and your target is very far away, you would like not to have exactly a matching, but you would like to minimize the effort in order to get as close as possible to the reference model. And this is a classical optimal control problem that you can solve actually in closed form. Okay, so this is a third application. And the last one, which I added on purpose here, and I should thank Cosimo della Santina, because I was reviewer of his PhD thesis, and he's in a very perfect position to speak to the whole community doing soft robotics, and this is why I asked him if I could steal a couple of slides, of course reorganizing in my way. But so he was considering, among the many other systems, robot with continuum deformation, so continuum soft robots, under some assumption. First assumption is that this can be approximated by a finite number of segments, each of which has constant curvature, but this curvature can be changed by control. Okay? So this is the first hypothesis. In this case, you see the experimental device that he set up, and there are 4 coordinates, which are not joint coordinates. You can call them curvature space, okay, the curvature space. And there are other assumptions, one on inertia, so you can represent the single segment by an equivalent point mass with a certain degrees of freedom. And finally, some infinitesimal distribution of stiffness and damping, which brings out this system to have a linear behavior in terms of elasticity. Now, what was realized is to move from a continuum, infinite dimensional system that you can still model, of course, but it's very hard to use this model for control purposes, to a system, an equivalent one, which takes the same form as a rigid system plus these two terms, one related to the stiffness of the device and one to the damping of the device, of the physical device, which is this one, okay? Now, the nice thing is that this system, although being soft, by construction is fully actuated. So you can do many things. You can cancel everything and go home. But a good idea is to preserve the physical property of the system. Otherwise, why did you set up or build such a soft robot if you want to stiffen it? Okay, that would be completely crazy. So, for instance, you can do the tracking case here. It means that you assign some time profile to the curvature of the single segment, and then you would like to have a control that even if you're starting with a different value, you have a transient, and then from some instant on, you track exactly those type of behavior. And this can be done in several ways. First of all, as a subclass, you may have a regulation task. So in the regulation task, the reference is constant. And in this case, if you just do a feed-forward action, which is k, the soft robot stiffness, not a different value, times the desired curvature, plus the damping of the soft robot, times the derivative of this, and you plug this expression into the closed-loop system, then you realize that your system looks like this, and it's exactly a robot without gravity under the action of a PD. Now, all students of a first course in control, robot control, should know that this is a global asymptotically stabilizing law, but it is in fact a PD control which is physically motivated, because you're not using a KP and a KD arbitrary, you're using exactly those of your system. So you need to model and identify this in the first place. And of course, if there's gravity, you can cancel gravity because you have full actuation, there's no problem. If you had under actuation, then the same problem that I've showed you for the elastic joint case would apply. And finally, if you want to follow a trajectory, you add more things. And in fact, the resulting aspect is a passivity-based control, not a fully feedback linearizing one. Okay, I think that I will skip this and just take to the conclusion. So I think that this idea of soft robots in any form has now a lot of interesting idea from the modeling point of view, from the application indeed, but also from the control point of view. Revamping old ideas and giving new suits to this concept. So in fact, we are looking in any case for simpler control law. Not because we are not able to implement complex control law, but because of computational times. This is not a problem, as I said, but because of really identifying a very good model, and this is maybe difficult. The other problem is the bottleneck due to sensing. Of course, we need to sense more, and if we don't want to sense, we need to use feed-forward commands, so inverse dynamic space. So in any case, we need to have a very good model. What about learning? I'm not an expert in learning, although I made some iterative learning control many years ago. So indeed, the feed-forward part in particular can be learned from trial. If you have a repetitive task, this is very easy because the same result holds for flexible manipulator, no matter if flexibility distributed in the link or concentrated at the joint. But of course, you would like to have a modern way of doing learning, so deep learning stuff that once you have performed many trials, then you can generalize the behavior. And then there are a lot of optimal control problem around, and if you like this type of topics, you can perform. Now, the other things is revisiting model-based control design. So model-based control design is not something that you should avoid, but in fact, do not fight against the natural dynamics of the system, and this is what I commented. You never build a system and then try to remove this. This was good in the 90s, where flexibility was a parasitic effect, and the only thing that you care is accuracy, fast motion on track. But now that this system are intended to share their workspace with humans, then you care about flexibility being there. But don't forget that the model is important, because with the model, you can still reach the performance that you need. Otherwise, you would give it away and rely only on learning is not the best way to do, in my opinion. And also keep in mind that this last system that I showed from Cosimo was fully actuated, but typically soft robots are underactuated, so not all motion are feasible. And the underactuation brings together a number of problems. One that I mentioned is the inversion of tip trajectory for the flexible links. In that case, you have non-collocation, and this inversion is not feasible. So even a feed-forward computation would fail. So there's a sentence, a word that I added in closing, which would deserve probably another lecture, which is input-output synergies, which in my terminology of control guy would mean that this system, even if you cannot feedback linearize them, but because of having many degrees of freedom, but only a few actuated, like the first, second, third synergy in the human hand or in the robotic hands mimicking the human hands, then with this limited number of commands, the best you can do is to select the same amount of output variable that you would like to control, and then you can do input-output linearization if you wish, keeping in mind that the internal dynamics should remain stable, or, and this is my suggestion, even input-output feedback equivalence. So without canceling things, but having that the input-output behavior of the synergy in actuation and the synergy in sensing, if you wish, matches a desired physical behavior. And of course, there are many other classes of soft bodies robots, hands, locomotion, and so on. So these I just scratched the surface of this problem. Thank you.
Thank you very much, Alessandro, for this very thorough exposition through the years and until the most recent topics. Are there questions from we have time for one or two questions. Yes. Here is.
So thank you so much for the very interesting presentation. I wanted to know your comment on the control of the same robot as Cosimo had, but with distributed load or arbitrary multiple loads at multiple locations. So how do you see these control approach in that case?
Well, of course, this model is particularly simple. And it's particularly simple not because you have this assumption of constant curvature of the single segment, because you can really go up with discretization as long as you have one local control for each of these segments. This is the main limitation. Now, if you don't have this, and or if you have some of this segment which are loaded by weight, so either you are able to model this, or you have to design a robust control. So, I mean, this was the easy case. This was just highlighting the fact that it's possible not to impose a desired arbitrary stiffness and damping to your system, but live with the one that you designed. In fact, Cosimo in his PhD thesis, he said also that the best thing to do is not really by control, but by design. Okay, so this is a kind like when you're designing Lyapunov function to prove stability. What comes first? It's a chicken and egg. No? So you design something, you look at the controller, it's too complex, you go back to the design, and so on. It's a co-design, actually, approach. So I'm not answering to your question, so I don't have any idea, but the general principle is there. So it's not impossible to apply those techniques, but one should look case by case.
Thank you very much for this very stimulating survey. I come to this from studying human motion. And of course, there are a lot of analogies with the nature of human actuators. I would say in human motion, there's less agreement that motion planning and control will be so separate. And so I'm asking here, essentially, if you think that only as a very limited class of potential motion plans would ever be controlled, does that affect your analysis? So rather than track, some arbitrary curve, if you, let's say, only track harmonic movements or have very simple space-time curves, is that something that is being taken into account in these kind of control analyses?
So first of all, although I have presented it very separately, feed forward or inverse dynamics, if you wish, and feedback, but they are intrinsically related. In fact, suppose that you organize a feedback as a lower level, so a reactive feedback, like I assume is quite present in the human body. Okay, and now the system that should move the limb or whatever with a feed-forward command needs to take into account the presence of this feedback. So this is really intrinsically related. Now, the other question about what is feasible and what is not, maybe we could have multiple human feasible motion, but we never explored them because they are energetic too inefficient or they are too dangerous for our muscle system or whatever. Okay, so these techniques allow you to say what can be done. Then the fact that it's worth to be doing or not, it's an open issue. It's an issue of what are your objectives. I've seen many work on trying to figure out what type of criterion is being optimized by the human while doing its motion. You have combination of several, but it's kind of a tailoring things, cut and paste of things. If somebody comes out with a general principle, what is behind that? That would, of course, be very useful also for robotics.
Very nice talk. Looking forward, the infinite dimensional case is really, I think, a very exciting topic. And a lot of the tools that you presented are actually dealing with finite dimensional systems. Yeah. And even in the case of in the last case, the problem had to be reduced so that you can apply tools from, I would say, standard control theory. So there is a fundamental question here, which is if you were to design, for example, an optimal controller for a system that is infinite dimensional, how much we should deal with the system? Should we go with should we do first a model reduction and then use standard tools from the control theory we have? I would say in this case, all of the issues of the model reduction will carry over to the tools that we're going to be using, right? Yeah. Or should we go the other way around, which in my opinion is the most courageous way, which is to develop optimization tools completely on the infinite dimensional space and then try to
implement it in finite dimension.
Discretize the solution. So what's your opinion about that, given the fact that there's going to be a lot of more computational power?
Sure. Well, let me say, are you familiar with the book of Balakrishnan?
Yes.
Yes. So I don't know if he's still living or not, but I mean, I'm glad that he's not listening to me right now. Because, of course, this competition between discretizing first and applying a finite dimensional controller, or keeping the model in its continuous version, in infinite dimensional version, design an infinite controller with partial differential equation and so on, and then implement a finite dimensional version of this, has been around for a while. Of course, the first method introduces the so-called spillover phenomena. So the fact that if you're not filtering properly your signals, then you will bring in whatever is beyond the bandwidth of your controller. The other way, it's more nice. I agree with this. But my question is the following. I've been working on a single flexible link with continuous methods. Not only with assumed mode, but really with a non-rational transfer function. And even then, when we're putting boundary conditions to this partial differential equation, you immediately introduce some approximation. If you have just one link with a payload, it's okay. But if you have two links, then you have, for every configuration, you have to change the boundary condition at the end of the first flexible link, which can be done in real time. But I mean, it becomes really, counterintuitive what you're doing. So what I'm saying is that although the second way would be preferable, even if, implementable, then the complexity of the problem when you go from simple case study to the real world, it's scaring me, and probably scaring most of the robotics research around the world. But I'm not saying that, again, there could be a finite solution, a definite solution at the end that handles with infinite dimensional cases. In fact, the property of non-minimum phase of a single Euler Bernoulli beam or a Timoshenko beam can be very nice interpreted with the infinite dimensional transfer function, better than with the finite dimensional one. So I agree with this. But from the control design point of view, the tools are not so developed as in the finite case.
Okay. So with this one, I think the audience is satisfied. Thank you very much for
Thank you.
the great talk.